Hello there everyone. In just a few seconds from the roller coaster on screen, you'll hear a very unique noise that you probably haven't heard before. Today, we're going to delve into where that came from and the propulsion mechanism used to generate it. That extremely satisfying high-pitched whine that you just heard was generated from LIMs and LSMs. These are linear induction and linear synchronous motors. They do have some differences, and we'll make sure to discuss those today. We're going to dive right into it with a little bit of history on this cool piece of tech. Now, pardon me if I butcher the name. However, Eric Roberts Laithwaite is mainly credited with the development of the linear induction motor, as he tried to push it to the forefront of the rapid transportation industry by attempting to use it as the propulsion mechanism for hovering trains. Prior to Laithwaite, a lot of the math behind linear induction motors already had a solid foundation from prior developments of rotary induction motors in the 1880s by Nikola Tesla and Galileo Ferraris, and many before them. This math applied well to linear induction motors since they function akin to the unraveling of a rotary induction motor. Note that with this unraveling comes a terminology change, as the stator, outer casing of the motor, is renamed to the primary, while the rotary shaft becomes the secondary plate. Alrighty-o. Now that you know a bit of the terminology behind these motors, let's get into how they work and the math behind that. For the first driving principle behind these, what we're mainly talking about is when you have conventional current flowing through a wire, that is positive to negative. In reality, electrons flow from negative to positive. What's actually happening is around that wire, a magnetic field is generated as represented by the direction of your curled index fingers. This magnetic field is in relation to the direction of the conventional current, in which your thumb would point to the positive end. An extremely similar rule can be applied to solenoids, helixes, or coils of wire, as your fingers represent the direction of conventional current flow around the coil and your thumb represents the orientation of the magnetic field. This is basically the principle of an electromagnet, which is kind of what these motors are. One last principle that applies in linear induction motors is how a changing magnetic field can create current. As much as I would love to explain this one in depth, I do not have time in a 5-minute video. Yet, the effects of these currents are important to mention. What happens is that currents are induced in the conductive secondary plate as the strength and direction of the magnetic field changes. The reason the magnetic field changes is because these LIMs, like most LIMs, are run off three-phase AC power, where a single phase runs into each of the three solenoids in an individual primary. Thus, due to the nature of AC power, the field generated around the solenoids rapidly switches direction. What you need to know is that the induced current in the conductive secondary causes the secondary to generate its own magnetic field. That, in turn, results in attraction and repulsion forces with the magnetic field of the primary, accelerating the roller coaster train. In contrast, a simpler motor style, which is becoming more popular nowadays, is the linear synchronous motor. This was the LSM I mentioned at the start of the video, not the LIM. What happens with linear synchronous motors is that every single primary must be activated at the correct time to first attract and then repel the permanent magnets of the secondary. These require much more complex control systems and as such are way more expensive, but the principle is somewhat simplified from a linear induction motor, which in turn gives these things the benefits of being able to be reversed in case a train needs to stop. Continuing to talk about the price tag on these devices, LIMs and LSMs don't just cost a lot to install, they cost a lot to operate. So let's just take a look at a simplified scenario here where we just have the Poltergeist roller coaster with its 6-car trains, so maybe about 6 tons, just being accelerated down the launch straight up to its maximum speed of 60 miles an hour, or 26.82 meters per second. From Google, we know that takes 3.5 seconds, so then either working through with kinematics and then using F net equals ma, or just taking a look and using kinetic energy of 1/2 mv squared, where we know the mass of the train up there, and then we know the final velocity of that 26.82 meters per second, we can wind up figuring out the amount of joules, then watts, and in turn amperage required to run just a single launch for these coasters, which normally cycle hundreds of riders an hour. And with this ride using 2,330 amps per launch, the cost can start to get kind of high. Overall, this has been a very fun video to make. I hope you guys learned a bit more about the math and history behind these linear motors, and I think we should end on a note that Eric Robert Laithwaite said himself, and he said it very well.
When used on the horizontal, and made in a much larger size, such a machine is capable of developing a very high acceleration.